Welcome to the first of two videos on systems of linear equations in Foundations of Mathematics and Pre-Calculus 10. In this video, we'll explore and apply what it means to solve systems graphically. The focus of the second video will be on solving systems algebraically. In previous grades, your child solved single equations in two variables. For example, when given the initial cost to buy a vehicle, as well as its fuel cost per month, they learned to express and interpret the relationship between cost and time as a linear equation. Further, they learned to represent and analyze this relationship through a graph. From this equation or graph, your child might have been asked to determine the total cost after a particular number of months, or how many months it will take to reach a particular total cost. Considering two different vehicles, say gas and electric, and their equations simultaneously creates a system of equations. A system of more than one equation allows your child to ask and answer new questions, such as, is an electric vehicle worth it? We'll return to this scenario later, but first we'll explore an example involving numbers without a context. Two numbers add to 12. What could they be? Take a moment to think about pairs of numbers that make this statement true. You might have offered 5 and 7, 10 and 2, or 0 and 12. Notice that we can represent these numbers as ordered pairs. We're not limited to whole numbers. We can think about pairs of fractions, decimals, and integers that add to 12. The number of possibilities is infinite. Let's consider a second different relationship. The second number is double the first. What could the numbers be? Again, take a moment to think about pairs of numbers that make this statement true. Here are just a few of an infinite number of possibilities. A system asks that we consider both relationships at the same time. That is there a pair or pairs of numbers that belong to both boxes that make both statements true? Press pause and give yourself some time to think about it. There is one and only one ordered pair that makes both statements true, 4 and 8. 4 and 8 add to 12, and doubling 4 gives 8. We can express each of these relationships as an equation. If we name the first number x and the second number y, then two numbers add to 12 can be written as x plus y equals 12. Similarly, the second number is double the first, can be written as y equals 2 times x. Taken together, these form a system of linear equations. Next, we'll analyze the system graphically. We can graph the first equation by determining the horizontal and vertical intercepts. If y is 0, then x is 12. The x-intercept is the point 12, 0. And if x is 0, then y is 12. So the y-intercept is 0, 12. Drawing a line through these 2 points shows all of the points that satisfy the first equation. Turning to the second equation, its graph passes through the origin. It also passes through 1, 2. Extending a line through these 2 points shows all of the points that satisfy the second equation. Notice that the slope, or rate of change, remains the same and can be used to plot additional points on the line. More importantly, notice that the point where the two lines cross is our solution from earlier. A point at which two lines cross or touch is called a point of intersection. This point of intersection represents the only x and y values that satisfy equations 1 and 2 simultaneously. Next, we'll explore a scenario that can be modeled by a system of linear equations. Look closely at the two candles. What do you notice? What observations can you make? What do you wonder? What questions do you have? I'll back up and play the animation again. You might have noticed that the candle on the left is taller. You might have also observed that the candle on the left is burning faster than the candle on the right. The difference between the two heights is decreasing. You might have wondered, how long will it take for the two candles to reach the same height? This is the question that we'll be investigating. It would be helpful to have more information, namely, the heights of the candles at different moments in time. This data can be collected, then organized in tables. When the time elapsed is equal to 0, the initial height of the first, taller candle is 20 centimeters. After 1 hour, its height measures 18 centimeters. After 2 hours, 16 centimeters. And after 3 hours, 14 centimeters. The initial height of the second, shorter candle is 16 centimeters. After 1 hour has elapsed, its height is 14.5 centimeters. After 2 hours, 13 centimeters. And after 3 hours, 11.5 centimeters. Let's represent the relationship between height and time graphically by plotting each set of data. The blue points represent the candle on the left. The red points represent the candle on the right. A straight line can be drawn through each set of points. Notice that these two lines intersect. Let's zoom in and take a closer look. What is the meaning, in context, of the point of intersection? Interpret this result in terms of the candle scenario. The two lines intersect when time equals 8 hours and height equals 4 centimeters. This means that both candles reach the same height, 4 centimeters, after 8 hours. Before we explore a different system of linear equations, let's delve into this one a bit more. What patterns can you find in the two tables of values? For each candle, can you write an equation that models the relationship between height, h, and time, t? The initial height of the taller candle is 20 centimeters. The initial height of the shorter candle is 16 centimeters. Every hour, the height of the first candle decreases by 2 centimeters. The height of the second candle decreases by 1½ centimeters every hour. Notice that for each candle, the rate of change is constant. This is what defines linear relations. The heights of the candles over time can be modeled by the equations h equals 20 minus 2t and h equals 16 minus 1.5t, respectively. Before moving on, let's take a quick sneak peek into the topic of the follow-up video, solving systems of linear equations algebraically. We're interested in figuring out when the two candles reach the same height. Equating the two heights creates an equation in one variable, t. Solving this equation gives t equal to 8. This will be explained in further depth in that follow-up video. Substituting 8 for t in the first equation results in h equal to 4. So too does substituting 8 for t in the second equation. Regardless of how we solve a system of linear equations, graphically or algebraically, its solution remains the same and can be expressed as an ordered pair. There are benefits and drawbacks to each method. We'll revisit this idea in the second systems video. But now, let's get back to graphing. We'll leave this scenario behind. Solve graphically. 2x minus y equals 5, and x plus 4y equals 16. I'll label these equations 1 and 2. One way to graph an equation is to determine the slope and y-intercept. We need to solve for y. First, subtract 2x from both sides of equation 1. Next, divide each term by -1. This gives y equals 2x minus 5. The slope is 2, which can be expressed as 2 over 1. We say that the rise is 2 and the run is 1. This means that there's a vertical change of 2 for every horizontal change of 1. The y-intercept is -5. Plotting 0, -5, and moving up 2 units and right 1 unit produces a second point on the graph. Continuing this pattern produces many more. Notice that we can also think about the slope as moving down 2 units and left 1 unit. Draw a straight line through these points to represent all of the points that satisfy equation 1. Turning to equation 2, first subtract x from both sides. Next, divide each term by 4. This gives y equals -1/4 x plus 4. The slope is -1/4. The y-intercept is +4. Once more, the y-intercept provides a place to begin to graph equation 2. The slope of -1/4 can be thought of as a rise of -1 over a run of +4. Alternatively, it can be thought of as a rise of +1 over a run of -4. Again, draw a straight line through these points to represent all of the points that satisfy equation 2. Notice that the two lines intersect at the point 4, 3. This point satisfies both equations 1 and 2. The solution to this system of equations is x equals 4 and y equals 3. Do all systems have one solution? We'll explore this question next. To help us make some generalizations and to speed things up, I'll keep the first equation the same and vary the second in each of the following two systems. What if the second equation were 4x minus 2y plus 6 equals 0? Once more, we can solve for y to determine the slope and y-intercept. Subtracting 4x and 6 from both sides of equation 2, then dividing each term by -2, gives y equals 2x plus 3. The slope is 2, and the y-intercept is 3. Applying this information, as we did earlier, produces the following line. Notice that the slopes of the two lines are the same, while the y-intercepts are different. The lines are parallel. They do not cross or touch one another. Therefore, this system of equations has no solution. Let's explore one more, again, sticking with the same first equation. What if the second equation were 6x minus 3y equals 15? Subtracting 6x, then dividing by -3, gives y equals 2x minus 5. Notice that equation 1 and 2 are the same. Each has a slope of 2 and a y-intercept of -5. Each point that makes up the first line is also a point on the second line. We call these coincident lines. What does this mean with respect to the solution to the system? Well, every ordered pair that satisfies equation 1 must also satisfy equation 2. An infinite number of intersection points means an infinite number of solutions. Let's review what we have found. A pair of lines can be intersecting, parallel, or coincident. Thus, a system of linear equations can have one solution, no solution, or infinitely many solutions. Let's take a closer look at the equations themselves. To make comparisons between each of these systems, I'll rearrange some of the equations so that all are expressed in general form. Remember, a coefficient of 1 or negative 1 can be implied. The ratio of the coefficient of y to the coefficient of x determines the slope of a line. Since coincident lines have the same slope, these ratios must be the same. 2 to 1 is equivalent to 6 to 3. Scaling 2 to 1 by 3 gives 6 to 3. The ratio of the constant term to the coefficient of y determines the y-intercept of a line. Since coincident lines also have the same y-intercept, these ratios must also be the same. Notice that multiplying 5 by the same scale factor, 3, gives 15. Parallel lines have the same slope. We can see that the ratios between the coefficients of x and y are equivalent. Doubling these values in the first equation gives the corresponding values in the second equation. Notice, however, that positive 6 is not double negative 5. This means that the two lines have different y-intercepts. Finally, intersecting lines have different slopes. The ratios of the coefficients of y to the coefficients of x are not equivalent. Let's apply our understanding of systems of linear equations. First, we'll return to the question, is an electric vehicle worth it? From the introduction. The cost c over time t of both cars is given by the following. Where does each graph intersect the vertical axis? What do these points represent? The red line intersects the y-axis at 0, 31,000. This y value can be estimated from the graph, but it's much easier to determine from the equation. 31,000 represents the cost when time equals 0. In other words, it's the initial cost in dollars of the gas vehicle. Similarly, the blue line intersects the vertical axis at 0, 43,000. That is, the initial cost of the electric vehicle is $43,000. Notice that the initial cost of an electric vehicle is greater than the sticker price of a gas vehicle. State the rate of change for each graph. What do these represent? The rate of change, or slope, of the red line is 1,500. This represents the cost per year of operating a gas vehicle. The slope of the blue line is 500. This represents the annual operating cost of an electric vehicle. Notice that the cost per year of charging an electric vehicle is less than the cost per year of fueling a gas vehicle. How many years will it take for the cost of both vehicles to be the same? When is it cheaper to buy an electric vehicle? The two lines intersect at 12,49,000. This means that it will take 12 years for both vehicles to reach a total cost of $49,000. After 12 years, the lower operating cost of an electric vehicle offsets its higher purchase price. The answer to, is an electric vehicle worth it, depends in part on how long you plan to own a vehicle. This model does not take into account other factors, environmental impact, for example. Up next, a second and final application. Place the numbers from 1 to 9 in the boxes below so that the system has no solution. Each number can be used only once. One approach would be to randomly place numbers in the boxes until the condition is satisfied. A more efficient method would be to use reasoning. Remember that if a system has no solution, then its lines are parallel. That is, they have the same slope but different y-intercepts. What if we placed 1 and 2 in the following boxes? It's these two coefficients that determine how x and y change in relation to one another. Keeping this ratio the same in the second equation will ensure that the slopes are the same. 1 to 2 is equivalent to 4 to 8. Notice that, up to this point, equation 2 is a scaled copy of equation 1. We should avoid applying this scale factor when placing numbers in the remaining two boxes. If we did, we'd get coincident, not parallel lines. As it is, this is not possible with the numbers that remain anyway. I'll go ahead and place 9 and 3. You may wish to confirm that this system has no solution by expressing each equation in slope y-intercept form. This gives y equals negative 1/2 x plus 9/2, and y equals negative 4/8 plus 3/8, respectively. 4 over 8 is equivalent to 1 over 2. Observe that the slopes are the same, but the y-intercepts are different. Can you find a different arrangement of number tiles that results in a system with no solution? How many can you find? Outside of this video, we invite you to play with the other two possibilities: infinitely many solutions or one solution. Next, we'll connect what and how we learned to your child's mathematics curriculum. This video addresses several learning standards in the Foundations of Math and Pre-Calculus 10 curriculum. In content, we learned about systems of linear equations. The curricular competencies describe what it means to do the math. Let's highlight a couple that were elicited in this video. We modeled with mathematics in two situational contexts, predicting candle height and comparing vehicle costs over time. In non-situational contexts, we applied an understanding of linear equations when we analyzed the number of solutions that a system could have and, later, reasoned to possible equations of a system given the number of solutions that it had. We hope that you enjoyed this video and found it helpful when supporting your child in their mathematics learning. Please check out the other videos in this series, especially part 2 of Systems of Linear Equations. Thanks for watching.